Hello, this is Ian Vogelesang, and this is the third in a series of 3 videos on the go statement in IV. In the first video, we learned how to specify a basic test step, a basic subinterval sequence, where the length of each subinterval is defined by the subinterval seconds parameter, defaulting to 5 seconds, and where the warm-up period and the measurement period are specified by the warm-up seconds and measure seconds parameters. Then, in the second video, we learned how to specify the focus roll-up, which specifies the granularity at which measure equals on or DFC equals PID options are performed, as well as the focus metric, which is the actual metric that's examined. And then in this third video, we'll learn how to specify the measure equals on or seen enough and stop feature, as well as the DFC equals PID or dynamic feedback control feature. When you specify measure equals on, then the warm-up period is extended as long as necessary to wait for initial transient behavior to die down, and the measurement period is extended for as long as necessary to see a subinterval sequence ending in the most recent subinterval that's at least measure seconds long, and where for each instance of the focus roll-up, the subinterval sequence comprises a measurement to the specified accuracy. And then the DFC equals PID feature is used to perform dynamic feedback control to vary the IOPS up and down to hit some kind of a target. With the measure equals on feature, there's 2 parameters to specify, and for example, in this case, we're looking to be 95% confident that we've made a measurement to plus or minus 2%. IV has a menu of 11 specific preloaded confidence values that you can pick from, and they're shown here, and they're taken from the Wikipedia page mentioned in the link here. Then there are several additional parameters that you can specify for the measure equals on feature if you have a command device. First of all, there's the max write pending feature. This defaults to 100%, but the example here, max write pending equals 2%. You might want to specify something like this if you're doing, let's say, a random read test, and you want to make sure that no previous test step has left write pending full of data whose D-stage activity is going to pollute your random read test. So if you specify the max write pending value, and here for max write pending it was 2%, that means that the warm-up period will be extended as long as necessary until write pending goes below 2% and stays there. Conversely, if you're doing a let's say a random write test and you know that you're going to go into emergency D stage, then you can specify the min write pending value. And here, when we specify a min of 67% write pending, then the warm-up period will be extended as long as necessary until write pending goes above that minimum write pending value of 67%. And this will ensure that measurement doesn't start until write pending is that full. Then the third write pending parameter is max WP change. And here you can specify the maximum amount that you allow write pending to vary up and down during a measurement. With DFC equals PID, we're dynamically adjusting the total IOPS, and please go to that Wikipedia page there to learn a little bit more about PID controllers or PID loops. The diagram on the left is taken from that page. In this case, we're operating on some kind of a feedback metric, and then we're controlling total IOPS using a PID loop. The feedback into the PID loop is the value of the focus metric that we learned how to specify in the second go statement video. This is either host workload data, such as service time, or it might be subsystem data, such as busy percent for parity group. In a PID loop, the error signal is the difference between the measured focus metric value and the target value. Then to generate the new total IOPS setting, there are 3 terms and 3 constants for you to specify. The P, or proportional factor, is multiplied against the error signal. Then the I, or integral factor, is multiplied by the sum of the error signal since the start of the test. And then finally, the D, or derivative factor, is multiplied by the rate of change of the error signal. And then these 3 terms are added up to generate the new total IOPS setting. If you don't specify a focus roll-up, it defaults to the all roll-up, and then the new total IOPS setting is in effect for all workload threads. Or you can specify a specific roll-up, and then the DFC equals PID calculation and sending out of the new total IOPS happens at the granularity of the individual instances of the focus roll-up. Then the PID loop mechanism works fine, but there's really very little guidance because I've only just got it working. There's no guidance on how to program the P, I, and D constants. What I've seen playing with it is that to plot a 20% busy curve of something typically requires using different PID constants from plotting an 80% busy something. So in your loop where you iterate over target values, you may need to adjust the P, I, and D constants according to each target value. For busy percent or service time, generally speaking, using the I constant alone and setting the others or leaving the others defaulting to 0 gives good results. If you wanted to achieve a target right pending, you would probably need to add a D constant to gate the rate of speed of approach to the target right pending. Then what I've found is that the PID loop works pretty well across a broad range of constant values, but you do need to sometimes tune a little bit. What we can see on the top diagram is a test where we ran several iterations, and on some of the test steps or subinterval sequence that are pointed to by this good call out, the PID loop operated stably and nicely made a measurement. But for some of the test steps or the subinterval sequence for the target value that we'd selected, the PID constants were such that the gain was too high and it was overcorrecting, and we saw oscillation here in the target metric. So in this case, at the top, if you see something like this on the PID chart, then you want to reduce the gain, reduce the value of the I constant in this case. And then in the bottom diagram, we can see a step here where in some of the iterations, some of the subinterval sequences or test steps, we had good PID constants. But here you can see at the bottom where the PID gain was too low, where 1,000 subintervals into the test, it was still taking its time, and it timed out before it actually locked on to the target value. So this, if it doesn't get up to the target value, then that means your gain is too low. So what I'd like to do perhaps in future is enable a sort of an automatic gain control feature in the DFC equals PID, where the DFC would look at the progress from subinterval to subinterval and would be able to recognize when you're getting these overcorrection oscillations, and it will reduce the gain, or where when the gain was too low and you just weren't approaching the target value fast enough, that it would increase the gain. So this is just an idea for the future. And that's pretty much it. It's fairly straightforward to specify the measure equals on and DFC equals PID features. And here at the end of the third Go statement video, I'm summarizing all of the parameters you can specify on a Go statement. You specify the step name to give it a meaningful name for your Excel graphs and charts. You can specify subinterval seconds, warm-up seconds, and measure seconds. And then you can specify the cooldown by write pending feature if you have a command device, which defaults to on. Then for the focus metric used by both DFC equals PID as well as measure equals on, there's a focus roll-up, which defaults to all, meaning that the measurement or the dynamic feedback control is performed for the whole configuration all at once. Or you can specify a specific focus roll-up, such as by port or by parity group, in which case the measurement or dynamic feedback control occurs at the granularity of the individual port or the individual parity group. The source must be specified as either workload or RAID subsystem. And then if you're specifying a RAID subsystem, you specify further the subsystem element and the element metric, and the subsystem element might be parity group and the element metric might be busy percent. Then for the source equals workload category, you specify category equals either overall or read, write, random sequential, random read, random write, sequential read, sequential write. Then you specify the accumulator type, which you look at either the bytes transferred accumulator, the service time accumulator, or the response time accumulator if you don't have IOPS equals max. And then you specify how you access that accumulator, whether you retrieve the average value that was poked in, or you look at the total number of IOs which are posted, or the min, max, or sum of the values that were poked into the accumulator, etc. Thank you very much.